Kaplan's, we're not doing Kaplan, we're doing Khan Academy's MCAT Prep Biomolecule Section Bioenergetics Questions. Okay, I think this is a very long question set, so let's hit it. The biochemical reaction A to B and back to A, reversible, has a large and positive change in free energy. So delta G is much greater than 1. Under physiological conditions, which of the following is the best estimate for the equilibrium constant KEQ? Is KEQ much greater than 1, equal to 0, less than 1, or greater than 1? Equilibrium constants. So we have a reversible reaction. It's in equilibrium. Delta G is way greater than 1, which means it's unfavorable. So what exactly is KEQ again?
So KEQ, that equilibrium constant, kind of looks at products and reactants. And so if it's 1 or closer to 1, that means that it's way favoring the products. And then if it's less than 1, it's going to favor the reactants.
Okay, so it is. So if we have a delta G of far greater than 1, then we are favoring the reactants thermodynamically, right?
I would say so.
So that would mean that KEQ should be less than 1. And yeah, we're right. Okay, very cool. All right, next question. The reaction A plus B, reversible, goes to C, is an exothermic reaction. If an equilibrium mixture of A, B, and C is heated slowly, what would happen to the concentrations of each species? All 3 concentrations would increase, A and B would decrease, C increases, all 3 concentrations decrease, or A and B increase, and C decreases. Okay, so we have A plus B, and then that's in a reversible reaction with C. It's exothermic. And then we heat it slowly. What happens to the concentration? So do you have any thought about this?
Yes, because I remember loving questions like this. So a good thing to remember is to go ahead and write out on your little scratch paper A plus B, double arrow, C plus heat. It's exothermic, so we can act like heat is just one of our regular products.
Okay.
And then use Le Chatelier's and say, like, if one side is increasing, then I'm going to try to revert back to equilibrium.
Oh, so reverting back to equilibrium using Le Chatelier's principle, my little seesaw that I like, we want to push up the other side, which means that A and B would increase.
Exactly.
And C would decrease, and that's the right work. Okay, awesome. So yeah, Le Chatelier's principle. Okay, which of the following best characterizes the free energy change, delta G, for an endothermic reaction under physiological conditions? Delta G is positive, 0, negative, or it cannot be determined. Okay, so if it's endothermic, meaning that, doesn't that mean that it's thermodynamically unfavorable?
Yeah, we would have to add some energy into that system for that reaction to occur.
So if we're adding energy in, then the G for the products will actually be higher than the G for the reactants.
Delta G is that like overall
right.
one.
So I meant like the G of products. Isn't it called a G Gibbs free energy?
Yes, but the equilibrium constant, I think, is what you're talking about, would be closer to 1 if we're favoring products.
Oh, I barely even understand what the equilibrium constant means.
Oh, well,
I wasn't referring to it.
I think you're mixing those up.
No, I'm saying that if you have to put energy into a system,
right.
If you're looking at like the classical catalyst looking thing where you have one energy site, another energy site, and then an activation energy that goes between them, the second energy site, if it's endothermic, meaning you have to put energy in, is going to be higher than the initial.
Yeah, so it's positive.
Right, because you're putting energy into the system. Okay, so we would expect the sign of delta G to be positive.
Oh, no.
Oh, it's not right.
Cannot be determined. I wonder if it's because we're taking into account temperature.
Free energy change, endothermic reaction under physiological conditions. Cannot be determined. Let's use the hints and see why. An endothermic reaction has a positive change in enthalpy. Change in Gibbs free energy for a biochemical reaction under physiological conditions equals the change in enthalpy minus the change in entropy times the temperature of the system. That's the equation. The sign of delta G cannot be determined without knowing the entropy.
Okay.
So you just have to remember that Gibbs free energy equation, and then you would know that you need to know entropy.
So I would, now we've done a couple of questions like this where them mentioning that it's happening in the body makes us pause for a little bit longer and does affect the answer a little bit. So don't immediately jump to, like we did, oh, it must be positive because it's endothermic.
Yeah, yeah. And also remember those formulas. Those basic formulas is probably like for chemistry, I'm going to say there's 30 or 40 that like if you just know what they are, you could probably recall them pretty quickly. Okay, if a reaction is exergonic under standard biochemical conditions, what must be true of the equilibrium constant for this reaction? KEQ equals 0, it is greater than 1, it's between -1 and 0, or it's between 0 and 1. So KEQ. So you were saying that if we have say it again. I really do not understand KEQ.
Yeah, so my thinking is that I'm sorry, it's like products over it's products compared to reactants, and that if our KEQ is over 1, then we're favoring products and that reaction tends to move in the forward direction.
Okay.
Whereas the opposite is true if it's less than 1.
Okay. Okay, so reaction is exergonic under standard biochemical conditions. What must be true? Well, I would have to think that means that it's more energetically favorable if you're letting go of energy. So it would be closer to 1 or above 1.
Yeah, that's the one I picked, above 1.
Okay, let's try it. Hey, okay, that was right. So yeah, if you're favoring the products, which in this case it says exergonic, so we think it's getting rid of energy in some way in the products, then you're going to be above 1 for the KEQ. Okay, next question. ATP hydrolysis involves the hydrolysis of what bond? The phosphoanhydride bond linking the gamma phosphate to the beta phosphate, the phosphoanhydride bond linking the beta phosphate to the alpha phosphate, the bond linking the alpha phosphate to adenine, or either the phosphorus hydroxyl group bonds on the terminal gamma phosphate. I'm thinking it's the bond linking the gamma phosphate to the beta phosphate.
I would agree with you. I'm looking in my head at that magnesium stabilizing the ones that aren't getting cut and the farthest one out getting chopped off.
Yeah. And it's right. Yeah, yeah. So remember, there's 3 phosphates on an adenine, so you'd have to assume that alpha, beta, gamma means that that's going out. That's how they name them. So yes, you would break the one that's binding the third one to the second, and that was the correct answer. Okay, next question. What is always true of spontaneous reactions? They increase entropy, they increase free energy, they decrease free energy, or they release heat. Spontaneous reactions, I think they release heat.
Yeah, so that exothermic, exergonic, however we say it.
Yeah. And,
Oh
ooh, it's not
no.
right. They decrease free energy. Huh. That's the correct answer. Let's look at those hints because I'm really not following that.
Yeah.
Okay. A spontaneous reaction has a negative change in free energy. Okay, spontaneous reaction, negative delta G. Yes. So we knew that.
Yeah. But I guess
Um,
we don't really understand what that means, so this is the definition.
right. A spontaneous reaction can consume heat if it increases entropy to a greater degree. Conversely, a spontaneous reaction can decrease entropy if it
Ugh.
releases enough heat.
That makes sense when we think about that equation.
Yeah, so that's the equation to really remember. Okay, a spontaneous reaction always decreases the free energy of the system. Spontaneous reaction always decreases free energy of the system because it's releasing it. Ah.
Well, so temperature could, because temperature, entropy, and enthalpy all vary.
Mm,
One could be higher as long as the second term is even higher, so that it ends up being negative. Like we could have different combinations of numbers. So all 3 of those variables can change as long as our overall, there's a
okay.
net decrease in free energy.
Oh, you're right. So okay, yeah. So the other ones like like releasing heat.
Would be the temperature variable.
Right, and that might not necessarily be true yeah, okay, you have to think about the whole package, that whole
Ugh,
equation.
yeah.
Wow, yeah, so that gives free energy. That's a real big one to remember. Okay, next question. A reaction X is exergonic and endothermic under standard conditions. What must be true of X under these conditions? So if it's exergonic and endothermic, that means that, okay, so the possible answer choices: heat of reaction increases, entropy is constant, entropy decreases, or entropy increases. Okay, so once again, this is knowing that formula. Let this be a lesson to everybody listening that you need to learn these formulas. Gibbs free energy. So we have an exergonic reaction, meaning that you're releasing energy, or rather, you're finishing with products that are at a lower energy state.
Yes, and then endothermic, meaning I have to put energy in
Right.
to start it.
You're putting energy in to start it, and so under these conditions, what is true if we know that we're going to have energetically favorable reaction, but you have to put heat into it.
So if I'm releasing energy in the end, it almost makes sense to me that something favorable is happening to some one piece of it, so maybe that means entropy increasing.
Yeah, I could dig that. Might as well check it. 1, 2, 3. Hey, we got it. Okay, but let's look at those hints real quick. An endothermic reaction has a positive change in enthalpy. Heat is consumed. Right. An exergonic reaction has a negative change in free energy.
Okay, so
exergonic.
I didn't know that distinction before. I didn't know that exergonic was for delta G.
Yes.
I guess I assumed, wow.
It was all thermodynamics.
Or that it was analogous to the exothermic.
Ah.
So not necessarily.
Yeah. Okay, so it says entropy must increase. And once again, everybody, take this lesson from us. The easiest way to have known that is just know that formula.
Yeah.
Okay, next question. What is the balanced half reaction for the reduction of nicotinamide adenine dinucleotide, which is better known as NAD+? Choose one answer. So we're looking for the balanced half reaction for the reduction, reducing it. Okay, so is it, and remember, reduction is gain. We're gaining electrons. GER, what is that? Gain electrons reduction? Leo GER and oil rig. I was an oil rig guy. Okay.
Leo the lion goes GER.
Yes. So NAD plus proton yields NADH. NAD plus proton plus 2 electrons yields NADH. NAD plus 2 electrons yields NADH. Or NADH yields NAD plus proton plus 2 electrons. So reduction. So we're gaining electrons, so you can immediately rule out that last one because you're not losing electrons.
Yeah.
Oxidation is losing electrons. So, and in the first one I read, so it's NAD plus hydrogen yields NADH. It specifically says H plus, a proton. So there's no electrons there to help this reaction happen. So I think that one could be thrown out as well. So we're left with either NAD plus a proton plus 2 electrons, or NAD plus just plus 2 electrons. I think we kind of have our answer here.
Yeah, I don't think you need to overthink this one. You could talk through it all the way, like if you were an oil rig person, or if you're a Leo the lion person.
Yeah.
Or you can kind of, using that biochemistry knowledge, recognize that anytime we're taking this precursor like NAD plus, and in order to add on that hydrogen, we have to have those 2 electrons that just form that little line that's the bond between the bigger molecule and that proton. So just recognizing that anytime we're sticking on a hydrogen, 2 electrons are following with it.
Yeah, because when you just have all these pluses lying around, there's no lines, like you said. There's no line that let the bond.
But it makes me very happy that you went through and you checked your math for all of those.
Yeah, absolutely. And we were right. So checking our math and thinking through things paid off. Strong work. Okay. Given that nicotinamide adenine dinucleotide, NAD, in its reduced form as NADH, is a key electron donating molecule, which we now know that those electrons were in that bond to make, with the hydrogen, is a key electron donating molecule in many metabolic reactions. Which of the following is a good prediction for the standard reduction potential, E naught, of the reduction half reaction of NAD? Okay, hang on. So we want to predict the E naught, the standard reduction potential of the reduction half reaction of NAD. Is it large and positive, less than 0, 0, or between 0 and 1? I would think large and positive.
Large and positive?
Yeah.
So large and positive on that. So every biology kid ever remembers seeing that long chart of reduction potentials, and you're starting with the most negative up top, and then you fall to the most positive at the bottom.
Right.
And at the bottom, I always remember there being oxygen on the receiving end. So I think we go from negative and to positive. I think that,
Okay.
you could easily switch this up.
And
But
in
I
this
said
case,
less than 0 because it is going to be the one that is giving.
So my thought here was that if you're talking about, I don't really remember that at all. I was just going off of just the words I was looking at. It says the reduction potential. So what is its potential to reduce? So
to be reduced, I think.
Standard reduction potential.
Right.
Oh, right. So it's potential to be reduced. So
Which
we have.
Is why. Oh, I'm sorry.
Well, yeah. So we have NAD, and we're trying to figure out how easy is it for it to be reduced. So if it was hard for it to be reduced, then it wouldn't be a very good molecule to be using in a lot of these metabolic reactions, because it's too hard to reduce the thing and it can't pick up electrons to bring into these reactions. So that's why I would have said it would have been large.
Large, okay.
Like a high up number, but I'm not going off of any amount of previous knowledge of it that.
I wouldn't have said that, so I'm going to guess mine, even though it might be incorrect.
All right, 1, 2, 3, check. I was wrong. She was right.
So,
less than 0.
Yeah, so knowing that, so then they write them backwards too, right? Because so this is the oxidized form, and so it's like the potential to be reduced would be like going from the oxidized form to the reduced form. So it's like written backwards. But NADH and FAD...
H2?
Well, yeah, that's the totally reduced form. I think just FAD...
Okay.
NAD plus and FAD are both at the top. And then we fall to oxygen at the bottom. And it has such a positive reduction potential that it wants to get reduced really bad.
Oh.
And so the values that we get at the top for NAD plus and FAD are, reversed. So they're going from oxidized to reduced. I'm talking in circles, but
I'm going to go to the hints because I'm not understanding anything.
Yeah, I'm sorry.
Okay. The standard reduction potential is a measure of the tendency of a chemical species to be reduced. Electron-accepting molecules like NAD have a strong tendency to be reduced under physiological conditions. The result is the electron-carrying molecule NADH. Okay, so electron-accepting molecules like NAD have a strong tendency to be reduced. So, okay, the result is NADH. So NAD has a strong tendency to be reduced. A good prediction for the standard reduction potential is that it's less than 0. So if standard reduction potential is the measure of the tendency of a chemical species to be reduced, why would NAD, which apparently has a strong tendency, be less than 0? What is that number at that point? If it's less than 0, how is that favorable? Do you have any idea?
No, I keep going back to that chart.
So in that chart, when you're up near the top with like NAD and FAD, what does that mean that they're up there, that they're the opposite of oxygen?
Because we work with it, like when we're working with oxygen, we know that is at the end of our electron transport chain, and it's way, way, way below all of the rest of like those two that are up top. And so it wants to get reduced much, much more. It has a much more positive reduction potential.
Okay, that makes sense. And maybe this might make some sense. So would this be kind of like we wouldn't want NAD to have a very, very large positive reduction potential, because that means it's kind of like if it was a really, really strong base,
Yes.
it would grab onto the hydrogen and not let it go.
Ah!
Okay, so we could think about NAD or FAD like it's a really strong acid or something, because really strong acid in any situation would let go. And that's what we want NAD to do. We want it to let go of those electrons for us.
Yeah, or like hemoglobin having an abnormally high affinity for oxygen, which would be detrimental to us because we need it to get into those acidic areas in our blood and be like, oh, this area needs more O2.
Yeah, and then let it go.
Yeah.
Okay, so that makes a lot of sense. Very cool. Okay, next question. A flavoprotein contains one FAD moiety. If this is the only electron acceptor in the flavoprotein, how many electrons can the flavoprotein accept when taking on its fully reduced form? Is it 4, 3, 1, or 2? Okay, so FAD. I know FAD can make FADH2.
Mm-hmm.
So if you have H2, then that's 4 electrons, right?
That's what I would have gone with. Yep.
So I'm going to click 4. Ooh, I bet it's 2. 4 was not correct.
No.
It is 2.
Why?
Okay, let's check those hints and see why. Okay, the fully reduced form of FAD is FADH2. The semi-reduced form of FAD is FADH. A flavoprotein containing one FAD moiety can accept 2 electrons in its fully reduced form.
I don't agree with that.
Huh. So does that mean that it's still keeping... Well, no, that's true. I mean, if it was... for FADH2, the hydrogen only... each hydrogen brought in 1 electron, right?
Yeah, yeah.
So that would be 2 electrons.
Okay.
Okay, I can live with that. I can totally live with that.
Yeah, I was just thinking about forming a new bond.
Right. Okay, next question. ATP hydrolysis under standard biochemical conditions has a delta G of way less than 0. Okay, so ATP hydrolysis, delta G is way less than 0. It's very favorable. Which implies which of the following about the reaction under these conditions? Is it the hydrolysis reaction decreases entropy, the hydrolysis reaction is spontaneous, the hydrolysis reaction is exothermic, or cleavage of the phosphoanhydride bond that occurs during hydrolysis does not require the input of energy?
Ah, this could be a trick question.
Huh. I think that's correct.
Okay, so I'm going to put the hydrolysis... Wow, I can't speak. The hydrolysis reaction is spontaneous.
Okay, so I really don't know. I'm going to try to reason my way through this. So the hydrolysis reaction is exothermic. That one kind of makes sense to me, but I don't know if you can say that. Or I don't know if you can say if it increases or decreases entropy. But spontaneous, that's kind of taking the whole thing into consideration. If we know that delta G is way less than 0, then I think that I remember, yeah, that someone saying that negative delta G means the reaction happens spontaneously. And then cleavage occurs during it does not require the input of energy. I don't know. I like yours though, because requiring the input of energy, I can't say for sure whether or not I understand how that works with the Gibbs free energy equation.
So even the breakage of ATP requires you to put in some amount of energy to break that bond.
Oh, but you get more out than you put in.
Yeah, so even though those phosphodiester bonds are kind of really unstable because of all the charges really close packed together, there's a lot of potential chemical energy there.
Oh.
It's not just going to spontaneously break off by itself. There's some input of energy, but that overall reaction is going to be, favorable.
Right. Okay, so it would be spontaneous. Yes, and that's the correct answer. Okay, yeah, so remember everybody, negative delta G, the whole reaction is spontaneous, even though you might not necessarily be able to talk about the individual parts. Okay, so the hints say cleavage of bonds always requires the input of energy. Okay.
That comes from TAing Gen Chem.
Ah, yes. All right, next question. Which of the following best predicts the result of raising the pH of an equilibrium mixture for the reaction ATP plus H2O is in equilibrium with ADP plus inorganic phosphate plus a proton? Okay, so which of the following best predicts the result of raising the pH of this equilibrium mixture, ATP plus H2O and ADP plus inorganic phosphate plus proton? Is it the concentration of ADP decreases, the concentration of ATP increases, the concentration of water increases, or the concentration of ADP increases? Okay, so we raise pH. What happens to this thing? So, Le Chatelier's principle.
Yeah, and this is also a trick question because they say raising the pH, and I don't care how long you've been doing chemistry. Sometimes when you're tired and you're stressed, you are going to think that raising the pH increases the amount of hydronium or just H plus ions, and be very, very careful.
It's the opposite. So, if we were taking away those free hydrogens that are on the right side of this equation, you could think about like you have a lack in that side of Le Chatelier's principle, so you would shift the equilibrium towards making ADP and inorganic phosphate. So it should be the concentration of ADP increases, and we got it. Very cool. I'm glad that we tutored. Okay, next question. Which of the following represents the numerator for the expression used to determine the equilibrium constant for the hydrolysis of ATP to yield AMP and 2 inorganic phosphates? Is it concentration AMP times 2 concentration inorganic phosphate, concentration ATP times the concentration of water, concentration AMP plus the concentration of inorganic phosphate squared, or concentration AMP times the concentration of inorganic phosphate squared? Okay, so I do not remember the KEQ equation. However, we might be able to reason our way through some of this. We want the numerator for the expression. So we want the thing that is going to make the equilibrium constant be greater, right? And you said, ooh, this is going to be the third time you said it, but I'm kind of forgetting each time, that when you have a higher KEQ, that means that the products are favored.
Exactly.
So if the products are favored, and we're talking about hydrolyzing ATP, we want the numerator to be the products.
Yep.
Because if we have more of the numerator, that means we have a higher KEQ. So if the numerator is the products, then that makes sense.
Yes, and so the thing here that I'm looking at these answer choices that I just don't quite remember like I should is I think that we take that 2 in front of the inorganic phosphate and we square it.
Ooh,
So I
okay.
think D is the correct answer. And just as a general note, for some reason I don't think we include liquids in these equations. So that could be some form of a trick question. If they included liquid, it wouldn't be included in your KEQ.
Is it liquid or just water?
Let's see, I don't know.
Like in an aqueous solution or something, they might talk about like you have to exclude the water component. I kind of remember something like that as well.
It's been a long time
Yeah.
since Gen Chem.
But let's see. I like your answer. Let's try it.
Oh, yeah, it is squared. Okay.
So the correct answer, once again, is the concentration of AMP times the concentration of inorganic phosphate squared. So our reasoning before was correct that you would want the products to be in the numerator because as that goes up, you get a higher KEQ, and that follows the rule. And then you take whatever the coefficient is for the inorganic phosphate or whatever it might be, and you move it up to the exponent.
Mm-hmm.
Okay, I like that. That was awesome. Next question. How does the free energy stored by ADP compare to the free energy stored by AMP under standard physiological conditions? Is it the free energy stored by ADP is positive and greater than the free energy stored by AMP, which is also positive? The free energy stored by ADP is positive. The free energy stored by AMP is negative. The free energy stored by AMP is positive and greater than the free energy stored by ADP, which is also positive. Or the free energy stored by ADP is negative and less than the free energy stored by AMP, which is also negative. Okay, so I think they both have to be positive.
Oh, okay.
Oh, I might not know. You're the metabolism person.
Well, I'm thinking back to that question that we just did that bit us in the hind end that was something along the lines of, a negative delta G is less free energy.
Oh, negative delta G.
Decreases free energy, so less.
Well, we're talking about delta G though at that point.
Yeah.
So delta G would mean.
But that's what free energy is.
Well, delta G is the change in free energy.
Well, yeah.
So that would mean that, like, if you have ATP and then ADP, ATP should have more free energy than ADP, so that as the reaction happens, you get a negative change in free energy.
Okay.
Because you went from more to less.
I'm not quite tracking with you, so I would have said the one that is negative and probably would have got it wrong. But that's what I'm going to pick because I have to be true to what I was going to say.
Okay, so let me try to find my answer. I want to say that the energy stored by ADP is positive, and greater than the free energy stored by AMP, which is also positive, and I'm going to click that.
Yep.
Hey, okay, that was right.
I would have missed it.
Yeah, so that's a good example. Just remember the difference between actual free energy and then the change in free energy. You definitely want the change to be negative. But if you have ADP, which let's just say arbitrarily ADP was at 10 free energy, AMP was at 5 free energy, the change is negative 5, even though they are both positive free energies in and of themselves. Okay. All right. Next question. Under which of the following conditions would one expect ATP hydrolysis to be non-spontaneous? A temperature slightly below 37 degrees Celsius. Okay, I think we can rule that one out.
Yeah.
A very basic environment, meaning high concentration of proton acceptors. No enzymes available to lower activation energy, or ATP concentrations very far below equilibrium concentration and ADP concentrations very far above equilibrium concentration. So we're talking about ATP hydrolysis to be non-spontaneous. So if we have very, very little ATP... Oh, God bless you.
Thank you.
So if we have very little ATP, then I don't think that would change the spontaneity at all. And the amount of ADP, I don't think that has anything to do to it. We have, okay, so then what about no enzymes available to lower the activation energy? Yeah, right? So all of these enzymes that are doing their other jobs, like for instance, the sodium potassium ATPase, isn't that technically a catalyst for ATP hydrolysis?
Yeah, and I'm trying to think, can this just happen freely in the cytosol? Because that, I'm just not sure. I know that's a really simple question.
And then we have a very basic environment. So how would a very basic environment change ATP hydrolysis? And would it make it non-spontaneous?
I almost feel like it would be easier to cleave the phosphate with something... Oh, maybe not, because they would both carry a negative charge.
Oh.
Like if I'm talking about hydronium and my ability to cleave ATP, I might not be able to get in there with another negative charge.
Oh.
And I think...
Oh, you need hydrogens to... it's hydrolysis, so you would have less water molecules, right?
Yeah, if you had more hydronium. I'm sorry, hydroxide.
Right. I'm going to say it's that. A very basic environment would cause ATP hydrolysis to be non-spontaneous. I'm really feeling that.
Okay, hold on.
Okay.
What did one explain?
So no enzymes available to lower activation energy. That's, my example, I guess, was a bit of a stretch. We can throw out temperature, and then ATP, ADP concentrations. That doesn't have anything to do with ATP hydrolysis.
Yeah, and I don't know if your answer was that far out there. I truly don't remember if it can happen on its own in the cytosol.
Okay. Well, I like a very basic environment. Let's check it.
Oops.
Ooh, it's not right. Is it the... Wow, it is ATP concentrations very far below equilibrium. Okay, so let's check this out with the hints. Okay, a non-spontaneous reaction has a fractional equilibrium constant. Fractional equilibrium constant?
I've never heard of that.
Are they talking about like the KEQ equation? That it's technically a fraction? So. Okay, a fractional equilibrium constant, one that is less than, it's less than 1 but greater than 0, arises when the product of the concentrations of reactants raised to the powers of their balanced stoichiometric coefficients, like we said previously, is greater than the concentrations of the product. So concentrations of the reactants greater than the concentrations of the products raised to the power of their balanced stoichiometric coefficients. Okay. One would expect ATP hydrolysis to be non-spontaneous when ATP concentration is very far below equilibrium concentration and ADP concentration is very far above equilibrium. So they're saying that this would cause ATP hydrolysis to not be spontaneous because you're going to have, it's going to be trying to shift equilibrium back to putting a phosphate on ADP.
Yeah, and I'm thinking I should have thought about this in terms of metabolism, which I'm finding is a really good trend to kind of go by. But I'm thinking even about glycolysis versus gluconeogenesis and like my steps at which I am regulating based on concentration of ATP and ADP. And so if I have, so if I'm decreasing the tendency to break up ATP, I'm going to need to build back up ATP. You know, if I have too much ADP, I would do gluconeogenesis and try to build up something that I can create more ATP from. So
that's
that
them
makes
fixing
sense.
that's so that would be how the body would fix like Le Chatelier's principle,
I'm not quite sure.
if that applies.
Yeah.
Well, it's important to remember, I suppose, that yeah. So this is ATP concentrations very far below equilibrium concentrations, and ADP concentrations very far above equilibrium concentration would cause ATP hydrolysis to be non-spontaneous. Okay, next question. ATP hydrolysis is a spontaneous chemical reaction under standard physiological conditions. What is always true of spontaneous reactions? That the products of the reaction have higher free energy than the reactants, the reaction occurs slowly, the reaction occurs quickly, or that the products of the reaction have lower free energy than the reactants. Okay, so spontaneous, that always means that you have a negative delta G, and therefore the free energy has to be lower in the products. I'm pretty sure. So I don't think speed of the reaction. I suppose that's kind of relative. It doesn't matter for the purposes here.
I don't think that tells us anything about the rate.
Yeah. So I think that from what I know, you just have to look at the energy states, and that spontaneous means negative delta G, and negative delta G means that the free energy of the products is lower than the free energy of the reactants.
I would say the opposite.
Really?
Yeah, because right, the like delta G, if I'm thinking about physics, like maybe like delta V, like change in velocity, I would do VF minus VI. And if I want a negative number, my second one has to be bigger.
Yes, so a bigger initial and a smaller final.
It's been a long day.
All right, let's check that. Okay, that was it. So the products of the reaction have a lower free energy than the reactants, which have a higher free energy. Okay, next question. Glucose is oxidized to what molecule during aerobic cellular respiration? Carbon dioxide, oxygen, ATP, or water? Okay, I think you're gonna know this one. Let me think it through. So, glucose. For everyone who does not know, I am not very good at metabolism. Do not remember any of it. Okay, but we have glucose oxidized to what molecule during aerobic cellular respiration? So when I saw aerobic, I looked down at the answer choices. I thought it's definitely not going to be ATP. I think glucose does not even have as many atoms as ATP does. Water, it could be because water is a product of making ATP. But when they said aerobic, I thought carbon dioxide, oxygen in, carbon dioxide out. So I'm going to say it's carbon dioxide.
And you would have been right here. So the big things with our energy deriving molecules, if you can even say that, so our fats and our carbs, would be the ability to take those large, bulky carbon-containing molecules and oxidize those into something like CO2, which we would then breathe out. So the more carbons you have and the less work you have to do to those carbons, the more energy you can get out of them, which is what actually makes fats a better long-term energy storage mechanism, especially something like a saturated fat, or I don't even have to remove any double bonds. I have more oxidation than I can do on a regular carbon with no double bonds, and I can get more energy out of that.
Oh, very cool. And we check it? Yeah, we got it right. All right, strong work. Okay, oxygen is reduced to what molecule during aerobic cellular respiration? Okay, so oxygen is like the opposite. Oxygen is getting reduced during aerobic cellular respiration. Is it water, ATP, carbon dioxide, glucose? Okay, there is only one answer you can have here, and it is water.
Very well done.
Okay, yes, because water is basically two waters would be one oxygen molecule completely reduced.
Exactly.
Okay, and we check it. Yep, it was right. Very cool. All right. Aerobic cellular respiration involves the flow of electrons from one chemical species to another. Which of the following best describes this process? Electrons are transferred from glucose to oxygen. Electrons are transferred from glucose to carbon dioxide. Electrons are transferred from oxygen to water, or electrons are transferred from oxygen to glucose. Okay, it's definitely not oxygen to glucose. Transferred from oxygen to water. It could be that. Transferred from glucose to carbon dioxide. I don't feel like you're oxidizing glucose to carbon dioxide, so so if anything, you're like losing electrons through that. Electrons are transferred from glucose to oxygen. Transferred from glucose to oxygen. You could be doing that because if you're putting electrons on oxygen, you're reducing it to water. I'm gonna say that's the right answer. Electrons are transferred from glucose to oxygen.
So Kevin mentioned I'm
boy,
sorry,
I'm
tall.
wrong.
You're actually right.
Oh, I'm right.
But the way you went about doing it, I think, is important. So the first thing he mentioned is, okay, this one. So he mentioned oxygen and glucose, and he was like, well, oxygen's at the end of ETC, so the electron transport chain.
Mm-hmm.
So I can't pick oxygen to glucose. That makes no sense. Okay, so ordered arrangement is important. And the other thing that's important here is considering reduction versus oxidation. So oxygen to water, I'm getting reduced here. So my flow of electrons would I'm reducing oxygen. Oxygen's not giving the electrons to water. So yeah, cut that one out. And glucose to carbon dioxide. Well, yeah, that's the correct order of how that thing happens, but glucose is getting oxidized. So again, I'm not giving any electrons to carbon dioxide.
Right. So yeah. So you have glucose. And then in the path of transferring electrons eventually to oxygen, you're creating. Oh, so literally the ETC is you take glucose and like energy from glucose, electrons from glucose rather, and they eventually make their way through the chain. And as they're going through the chain, they're providing the energy to create the proton gradient. And then eventually at the very end, they go to oxygen to make water. And that's just enough of a proton gradient to cause ATP hydrolase.
I think they just called it ATPase. You can also call it complex 5 of the ETC. It's a less used name for it, but it both of them work.
Okay, so that's like the whole path. That's the whole point. Wow, I'm having like an absolute like revelation here about
and
about
oftentimes
energy.
you do with metabolism. You're like, oh my gosh, this one is connected to this one for X, Y, and Z, and then both of them make more sense.
That was a really good question, and we got it right. Wow, Sal Khan, thank you very much for that question. I love that. That was just dandy. But we're going to the Thunderdome. The very last question. Thank you all for staying with us for so long. This has been the strongest work I could imagine. All right, last question. Which of the following best describes the respective free energy changes for the one-step combustion of glucose in the presence of oxygen, as compared to the multi-step oxidation of glucose during cellular respiration, assuming both reactions occur under identical conditions? Oh, I guess they had to put a question mark at the end there, but that was kind of a weird place for them to do it.
Yeah.
Okay, so we want to know free energy changes for a combustion reaction versus a multi-step oxidation reaction. So, is the answer the combustion has a higher change in free energy? More information is needed to answer the question. The combustion has a lower change in free energy, or both reactions have the same change in free energy. So, first thing that comes to my mind is, did they tell us amounts? Because they say a one-step combustion. So combustion reaction, you take a carbon source and you take oxygen and you produce water, carbon dioxide, and heat.
Yeah.
So that's assuming that you're taking glucose and you're using every single carbon in it, and you're completely oxidizing those carbons. So that's as much energy as could possibly be in there. During cellular respiration, if you take a single glucose, you're doing the same thing, right? You're utilizing every single carbon.
Yeah, I'm not exactly sure what they're asking here. I would think that so saying one-step combustion of glucose, okay, maybe I have to put in less energy because it's just a one-step mechanism. But then I think with my ETC and going through the Krebs cycle and starting from glycolysis, like, yeah, there are a couple of dehydrogenases in there that need ATP to do their job. But overall, I produce like 36 or something crazy ATP.
Ooh. So I think I see something that you're saying that I might have a little bit of insight on.
Okay.
So you were saying that like how much energy it takes in the like intermediate steps.
Yeah.
So here, all they asked for is the respective free energy changes.
Right.
So I would think, I might be wrong, but I think all they're looking at, if we think back to our Gibbs energy like curve with the catalyst,
Yeah.
all they want to know is that the line that you start with and the line that you end with on the graph, which one is bigger? The stuff in the middle, like getting up to that activation energy, that would be all of that like extra energy that you need to put into the system. But I don't think that's what they're looking for. I think all they care about is that however much you start with and however much you end with. So do you know, does a single glucose molecule, does every carbon in it get used?
For the pathway of metabolism?
Yes,
Yeah.
for multi-step oxidation of glucose.
Yeah.
Okay, so every single carbon gets used.
Yes.
I think they're the same.
Okay.
Same change in free energy, because we start with the exact same glucose, and in one, we create 6 carbon dioxides, or 6 or 7? No, 6 carbon dioxides, and then water, and then in the other one, which is the multi-step oxidation, which I'm less familiar with, but as long as we're using every single carbon, I think we produce the same amount of carbon dioxide. And
I'm going to stick with what I was going to say because I'm not going to have you on the MCAT and I might get it wrong. But
what were you going to say?
the combustion has a lower change in free energy.
Okay. Well, shall we?
Ugh.
1, 2, 3.
Oh, no.
Oh, okay. I was right. Okay, but let's check those hints real quick to make sure that my thinking was correct and I didn't just guess that. All right, the multi-step oxidation of glucose during cellular respiration results in the same products as the one-step combustion of glucose and oxygen. Free energy is a path-independent, meaning... Wait, free energy is path-independent, meaning that it is a quantity that depends only on the initial and final state of a chemical system. Okay, I was thinking the right way. Both the combustion of glucose and the multi-step biochemical oxidation of glucose have the same change in free energy. Yes, so that's a common theme through all these bioenergetics questions. They're going to ask you about change in free energy versus actual potential or inherent free energy of any individual molecule.
So could we also call this a state function?
A state function?
Where they just worry about the beginning and the end and how you get there in the middle is not super important?
Yeah, absolutely. Yeah, if you're talking about the change in free energy, the differences between start and ending, it really doesn't matter what you do in the middle.
So I think I let my knowledge of metabolism let me think through it way too much. I think I needed to focus more on what exactly they were asking me.
Fine dining and breathing. Strong word, gang.